rockets, which you might expect are forming stars. So in a model where you take a galaxy to have a uniform temperature, this is sort of the right question to ask. But in a practical situation, this might not be. With that said, it's the bit of observational evidence I have, and so it's kind of the only thing I can show, right? So I think the point is, if we're really optimistic, what we might hope is this gives us a mechanism for something that might look like the star-forming main sequence. Okay? And that's actually only one of, I mentioned there are several different solutions here. I should point out there are a couple other solutions to these equations that also might be interesting. So one is it could be that it's the IMF that wins instead, right? That this top heaviness or bottom lightness ends up winning. You actually make more cosmic rays, and now the temperature continues to increase, and you're going to get a runaway solution. Okay, and this solution also at least is mathematically possible. Physically, what would this look like? Well, it's actually going to be a low star formation rate galaxy, but it's going to be a high star formation rate of massive stars. In this case, by massive, as I was showing you kind of earlier, really everything sort of solar mass and above, you're making the same IMF with the same slope, but just you don't make the low mass counterparts, right? So the ways that we have of measuring star formation rate currently generally come from the high mass end. This is going to look like a very high star formation rate galaxy. It'll be very metal rich, it'll have a lot of hot dust. And so one possibility is that this is actually something that could describe starburst galaxies. Except that if this is the right mechanism, the starburst galaxy is actually a misnomer. It doesn't have such a high star formation rate, it just has this burst of massive star formation, right? So the hope, though, is that maybe if we're lucky, right, we can build a model and you get two solutions. You get sort of this attractor solution and this runaway solution. And I'll put the fine print real small in the hopes that no one will notice it and you won't read it, that we're kind of hoping that the boundary between these is at a reasonable temperature and that the numbers work out, and we don't really know if that's true. But if we're really lucky, we kind of have these two solutions, right? One sort of main sequence-like and one starburst-like. And at least qualitatively, we do actually make a bunch of other predictions, which we can kind of test and which look reasonable. So for example, one of the things that we discover is that you actually naturally want protogalaxies to be very compact, because in order to be on this main sequence-like solution, instead of to hit the runaway one of the things we also end up requiring is a high enough gas density to stay in equilibrium. So that if you have a range of different gas densities and you try to get very high star formation rates, only the central region of the galaxy with high density will be able to make stars efficiently. So if you just count starlight, high redshift galaxies will look very compact. And this would have an observational signature, that if you look at something like a 21 centimeter galaxy cross correlation and try to estimate size of H2 regions, we'd actually predict that there's gas extending much further out beyond the protogalaxy than the light distribution would infer. Okay? Another thing that can happen, right, is in this tail, we get to the point where the cosmic rays don't dominate, right? And I mentioned that there were a few different solutions here, right? One possibility is a constant temperature case where the cosmic rays don't dominate. And it turns out that then there's a different equilibrium solution, right? Because zero everything is also equilibrium, right? No star formation, no temperature, no cosmic ray contribution. And it turns out that when you add this extra input, that's the one that becomes the attractor. And so maybe what this means is that if you can make a mature quiescent galaxy, it actually sort of wants to stay there, even if you give it a fuel supply later on. So I think the point is that we sort of get this hint that qualitatively, if we just take this toy model and we put cosmic rays in, we ignore everything else, we ignore all the complexities of the galaxy, we ignore all the things that we know must be important in the problem, suddenly you get a lot of interesting behaviors. You get a bunch of the phases that galaxies go through, you get them in the right order, you get sort of these similar evolutionary histories for galaxies at a common mass, okay? We also, because we have this top-heavy IMF, predict that the mass-to-light ratio, and therefore both the stellar mass and the star formation rate, are overestimated. And that this is true at very high redshift, so it maybe helps us with these impossibly early galaxies. It's also, by the way, true at very low redshift, right? So in the Milky Way, most of the stars were made not at low star formation rate, but earlier on at high star formation rate. So it would mean that we'd be overestimating stellar masses of local galaxies as well, by a similar token. And this perhaps has interesting implications for things like dark matter distributions that we infer from local galaxies and clusters. Because if we're overestimating the baryons, then for a cuspy profile, this makes no difference because the dark matter dominates everywhere. But for the ones with core profiles, the baryons start to dominate in the center. And so this actually would mean that if we're overestimating the stellar masses, there's more dark matter in the central regions of these galaxies and clusters than we expected. So there may be a few of these different hints, but one of the things I'm hoping to do is to ask some experts. Hopefully some of the people in the room can tell me whether there are some important things we're missing here. Because otherwise the next step is to really try to figure out how to treat this properly in numerical simulations. And the reason that hasn't been done is because cosmic rays are just inherently very complex to model. They require many different scales. And now we care about the interactions between cosmic rays and everything else that's going on. So I think that's most of what I want to show you. The last thing I want to do is just very quickly mention that we now have a summer research program that NSF is funding, meant for undergraduates plus first and second year graduate students, basically anybody that doesn't yet have a master's. Some of the excellent work that Josh Spiegel did as an undergrad was a similar kind of program, and if anyone has some students that they want to recommend come join us, then the application deadline is February 1st, and we'd love to have them. So yeah, thanks for inviting me. Sure, I don't know how you normally.
Okay, so at least in my impression is that the most popular explanation for the main sequence at redshifts 0 through 3 is that it's regulated by the stochasticity of gas accretion and feedback. I don't naively see a reason why that wouldn't be the case at high redshift. And so my question is, what makes you think that cosmic rays are the answer instead of just feedback?
So one of the problems with stochasticity, I'm trying to think if I have that slide. Okay, I don't have that slide available. One of the issues with stochasticity, okay, yeah, I'm gonna try it this way. So let's say you take it on.
Just like get rid of the stochasticity. Just say like accretion and feedback. Why can't it just be accretion and feedback like it is at low redshift?
So I think the issue is that if it's going to be accretion and feedback, the problem is making the right kind of attractor solution. So one of the puzzling features of the star-forming main sequence, we usually show the star-forming main sequence as having small scatter in the sense that at fixed redshift, there's a small scatter in star formation rate.
Oh, that's small.
0.2 dex or something, yeah. One of the other ways that I could have described the star-forming main sequence is that now that we have the redshift evolution, okay, another way that I could say that is that if you give me the properties of a star-forming galaxy, give me, say, its stellar mass and its star formation rate, but don't tell me the redshift. How well can I recover the redshift? And the answer to that turns out to be to within 1 to 1.5 gigayears across most redshifts, but more importantly, about constantly so. And so one of the things that that's telling us is that galaxies don't actually have kind of divergent histories. They have to have similar looking histories. And one of the problems with something that's predominantly stochastic or predominantly driven by infall is that if it's really directly driven by that, we would expect an ensemble of galaxies to have more and more different histories, meaning that the scatter of the star-forming main sequence, at least in time, ought to be spreading out toward late times. I don't want to say what it would do in star formation rate because that's kind of not quite the right measure here, right?
But all the simple model, it works in all the simple models. Like you recover the right scatter. Like in all the toy models that are just accretion and feedback. Like a bathtub model or something. I know that's not
Right.
fashion these days, but like it all works.
Well, but for something like a bathtub model, what you're doing is you're matching it, you end up having to match it by tuning the infall. Right? So in other words, what you're saying, which is correct, is that if I give the infall the right set of properties, then one thing I can do is give it the right infall rate and that'll predict everything else, right? So if you prefer, we could turn the question into why is it that these different galaxies under different conditions all end up with similar looking infall rates? And if you can come up with a model that would predict that, then I don't think you would need feedback later in the process, right? The approach here is essentially to say we do expect that galaxies in different environments ought to have very different infall rates. If you just take something like a bathtub model, this would naturally want to drive them to have different histories because they tend to use up the gas that's available. So therefore, we want a mechanism where even for different gas supplies and different infall rates, they'll still be driven to similar behavior. But I don't know that that's the right approach. It could be that instead it's on the environmental end. For that matter, it could be that, for example, the relevant infall isn't all gas, but it's just pristine gas, or it's just cooling gas. And so if a merger gives you a lot of hot gas, but there's some rate limiting step to the cooling, maybe it actually doesn't matter whether you're having the merger right now because there's some surplus of gas that could cool. So I would definitely agree this isn't the only approach. The thing I was surprised about is that if you take out all these other complexities and just look at the cosmic rays in isolation, all these things pop out.
Just
right?
to like cosmic rays in your language are really just a mechanism that distributes temperature.
Yeah, that's right. It's really just a temperature distribution mechanism from.
So it's
yeah.
like a very specific term for something maybe slightly more general, right? Because you could imagine other